Okay, here we are, 11.2 day number 1. We're going to talk about law of cosines today, but first let's concern ourselves with the law of sines. Let's talk a little bit about this. This is what we talked about yesterday. Let's imagine this thing we'd call the height, right? We could find that height by taking the sine of A, right, and multiplying it by B. Right? So here's the height. How many triangles would we have if A was less than the height? 0, right? We just have the T-Rex arm. That wouldn't make it. So 0. How many did we say we'd have if they were equal? 1, correct. What kind of triangle would that be? A right triangle, correct, because this side right here would rotate down and be the same as the height of the triangle, which would make it a right triangle. Cool. What if it's greater than the height but less than the side B? Yeah, then that's 2. So if this were A, right, it could be either that or that. So we could have 2 triangles formed. So I'd have triangle 1 and triangle 2. We called this beta 1. We called this beta 2. Okay, and beta 1 and beta 2 have a special relationship. They are, as we call mathematically, supplementary. They're supplementary angles, so they add to 180. Now, alpha will never change. Neither will side B or side A. Right, so alpha will be the same, side B will be the same, side A will be the same, but this gamma will also change. That'd be gamma 1, that'd be gamma 2. Okay, so there are some that are consistent and others that will vary. What if A is greater than or equal to B? How many triangles? Yeah, then there's 1, right? So if this is B, this is alpha, here's A. If A is greater than the height and greater than B, we'll have 1 triangle, because if we tried to swing that over here, we wouldn't have another triangle. Okay, so there's 1 triangle there. Okay, so what does the law of sines do for us? It allows us to find a side or an angle. And if you have the ambiguous case, which is the case where you'd have 2 triangles, then you're going to have to find through not just 3 angles and 3 sides, but 6 angles and 6 sides. But not really, right? Because we already said that these values won't change, right? That and our angle right here won't change.
So really,
All right, so it'd be 5 angles, right?
5 angles, 1, and 2 eighths, I guess.
Right. Oh, hello. Get away. Pause. Okay, so let's continue. Next slide, please. There we go. Do you remember our concerns with if we have an obtuse angle? What would happen if A was less than B? No triangles, none. Right? And if A was greater than B, let's extend it out a little bit, we'd get 1 triangle right there. Okay. So the first thing I would do is I would look to see if I have an acute or an obtuse angle. If I have an acute angle, I'd find the height. If I have an obtuse angle, I would just look directly at A and B. A is the side across from the angle, B is the side next to it. So with a neighbor, I want you and that person or people to figure out how many solutions would there be. How many different triangles? 0, 1, or 2. So take 4 minutes and determine that. All right. Hey, let's have a talk here. First thing you should always do is compare A, side A, to your height. If it's shorter than the height, no triangle exists. So do we have a no triangle up here? Yeah, in number 2, right? Because 3.5 is less than 6. I can say no solutions or no triangle exists. Oh yeah, I'm sorry. I got it flipped. My bad. There's 1 triangle there. There's 1 triangle. Why? Because A is greater than B, right? So in that case, I didn't even need to find a height. Yeah, it's idden-ish. Vitayo. I don't need no stinking height because the angle is Well, it wouldn't be, obtuse wouldn't apply here, but you know what I'm saying. Yeah, you're with me. Admishbatai. Okay. Okay, so we have one triangle there. One triangle because A is greater than or equal to B. Okay, cool. Let's look at the first one. Is A greater than the height? Yes, so A is greater than the height. Is A less than B? Yes, so how many triangles are there? 2 triangles, cool. So 2 triangles exist. All right, we can go through that one if you'd like to with the ambiguous case, finding those 2 triangles. Number 3, how many triangles? 0, that was the one we were looking for, right? Because A is less than H. So since A is less than H, it won't reach. We'll have a T-Rex situation. I'm going to try to draw a T-Rex. Trying to tie its shoes. It's walking. And it just can't reach. It's trying, but it can't reach. Right? No triangle. None. No triangle. Okay. Wow, this acronym. I don't need no stinking height because the angle is obtuse. Okay, you don't have to find the height. All we have to do is compare A and B, right? If it's obtuse and A is greater than B, we have 1 triangle. If A is less than B, we have 0 triangles. A is greater than B. Therefore, we have 1 triangle. So 1 triangle exists. Cool. Okay, so here is the first example up there. We've turned this triangle on the left into the one on the right by just rotating. You see how that happened? Okay, same properties are applied. We still have the opposite side is 100. The adjacent side is 125, and the angle given is 40. So let's talk about that. Of course, law of sines would tell me sine of A over A would equal sine of beta 1 over 125. Could you find beta 1? Yes. Once you have beta 1, you could find gamma 1. Right? Because alpha, which is 40 degrees, plus beta 1 plus gamma 1 would have to equal what? 180. Cool. So then I'd know gamma 1. And of course, I don't know C, but once I've found B, or beta 1, I can find gamma 1. And once I've found gamma 1, then I can cross multiply and solve to find C. Okay. Now, how are beta 1 and beta 2 related? What's the link? Those two, right? They're supplementary. So in order to find beta 2, I would take 180 and subtract beta 1. And now I do the same thing in the other triangle. What's true is then that alpha, which we know is 40, plus beta 2, which we know would be 180 minus beta 1, has to equal, oops, I'm sorry. Oh, that was great. Has to, golly. Plus gamma 2 has to equal 180. And then the rest from there is cross multiplication and simplification. Which triangle here cannot be solved using the law of sines? What was the scenario that we had that we'd use the law of sines with? An angle with what? A paired side, right? A side across from it. Well, I don't have the side across from it. This would not work. Right? That's going to be a law of cosines situation today, which you'll see. In part B, or the second one, that's also a no because I don't have an angle at all. That's going to be a law of cosine situation. Over here, part C, is that law of sines? Yes, it is, because I could take 25 and 30, add them, I get 55. I subtract that. That does not make any sense. But that is a 125-degree angle, apparently. Well sketched, yep. I'll blame that on myself. So yes, that would be a candidate for the law of sines. Okay, now I want to get to probably one of my favorite proofs of the year. where I prove the law of cosines. You guys remember the forms of the law of cosines? C squared equals A squared plus B squared minus 2AB cosine of the angle C, right? I'm going to prove it right now. You probably saw it right here and just repeated it to me. Thank you. Oh, you didn't? Okay. There is an alternate form. To find the angle C, I'd take the inverse cosine of A squared plus B squared minus C squared over 2AB. That's to find that angle. So take a look real quick at this and tell me what my unknowns are. What's my unknown in the first one? A side. That means, what do I know? I know two sides with the angle that exists between them. That is a side angle side relationship. If you ever have a side or two sides with an angle in between it, you can use law of cosines to find the side across. So that would apply to this situation here. This is side angle side. What is this one? Side, side, side. Okay, that's going to be our second scenario. What is our unknown value? Well, our unknown value here is an angle. In order to find an angle, what do you need to know? You need to know, oh, that's a 2, don't do that. You need to know the three sides, right? So that's a side, side, side scenario. So let's prove it real quick. I'll just do one part of it. And then you'll probably be like, can I use that at my family reunion? Yeah. Okay, so I split the triangle that was listed above into two triangles. And I called the height h, go figure. And I called these two segments x and b minus x. So if I took and I added b minus x to x, I'd get b. Okay? So some genius figured that out back in the day. Not me, that's for sure. Okay, if I used right triangle trig, the cosine of c would be x over a. So what would x equal? Well, it'd equal a times the cosine of c. Okay, then they thought, hey, our friend Pythagoras was nice to us, gave us this theorem that said a squared plus b squared equals c squared. So x squared plus h squared equals a squared, which means h squared equals a squared minus x squared. Those are setup steps for over here. Notice that Pythagorean theorem is used again. C squared equals h squared plus b minus x squared. Okay, so I can do a direct substitution. Look what h squared is. I'm going to plug it in. That's a squared minus x squared plus, what do you think I'm going to have to do here? Your favorite four-lettered F word, FOIL. Yeah, FOIL. So you're going to get this. B squared minus 2bx's plus x squared. Oh, get ready for the fun. This is where it gets beautiful. I notice that something's going to cancel. A negative x squared and a positive x squared. Guess what? Cha, they're gone. So I have c squared equals a squared plus b squared minus 2b. What is x again? X equals a cosine c. Oh, it's starting to look familiar. I'm going to rearrange it, clean it up, and then you're going to say, what? I forgot to wear my glasses. Hold on. A squared plus b squared minus 2, commutative, move them around, ab cosine of c. Is that impressive? Are you like, wow, that's great? Thank you for the fake enthusiasm. So if I rearrange this to get this c all alone, I could get this in a different form. I'd subtract a squared and b squared. And then I'd divide by negative 2ab. Well, if I divide by a negative, that changes the sign of everything in the numerator. So that equals cosine of c. But if I want c, I take the inverse cosine of that. And when I rearrange it, look at that. Here are our two forms of the law of cosines. Isn't that just pretty? Hi. So this one right here, This is side, angle, side. So I'm going to use this one. What do I want to call angle C? Well, the only angle I got. The only one I got. Well, I'm trying to find side C. The only side I'm looking for is that one. So in using the law of cosines, you should only ever have to use it once. Ever. Law of cosines once and then law of sines from there. Because it's annoying, right? That's a lot of work. So for A and B, does it matter which one I call which?
No.
No, it doesn't. So I'm going to call this A and this B. Okay, so in for A, I'm going to plug 16.7. I'm going to square it. I'm going to add it to 13.5. I'm going to square that. I'm going to subtract 2 times 16.7 times 13.5. I'm running out of room. And as long as I don't mess that up, I should have C squared. Now, of course, you're going to have to take the square root of that thing. So C would be the square root of whatever this thing was, right? So I'd get something, and then I'd take the square root of something, and I'd get C. Should we see if we can do that without messing it up? Take out your calculator. I'll do the same. If you were to do your arithmetic right, it looks like C equals 9.8. Make sure and take the square root, right? All right, don't forget to take the square root. That's where a lot of mistakes happen, okay? So 9.8 would be that side. Does it make sense? It does in the reference of the problem. Like if you see a 96, some kid's going to write 96 here and be like, I got 96. And you're like, not possible. Hello, you got a 16.7 and a 13.5. No way that's going to reach, right? So go back to the problem, look at it in the context of the problem, and figure it out. Over here, this is the setup I would do. It doesn't matter what I call these. I could call them A, B, and C in any order. And then all I'd do is the inverse cosine of A squared, looks like 9.8 squared, plus B squared, which I've got 24.1, minus C squared. It's pretty amazing that you can put them in any order because, well, that's just amazing to me. But I think weird things are amazing like that. And you should get an angle. If you get an angle that's above 180 degrees, you got issues. If you get a negative angle, you got issues. So you should get a value between 0 and 180. I would assume that this angle would be less than 90. That would be a good assumption, right? Seeing that that side, oh wait, hold on. Which angle am I finding? Across from 18.5, so I'm finding that. So I would say, yeah, it's going to be less than 90. What do you get? 44 point what? 9? Okay. So you can confirm that at home on the web. Like, comment, subscribe. This is Math Magic. Enjoy your evening and homework.